Hello everybody and welcome to our Chapter 8 lecture on confidence intervals and one population mean. As a reminder, this is meant to supplement the discussion from the authors on the Chapter 8 confidence intervals and one population mean. My goal is to supplement that lecture material with a discussion on how to find our confidence intervals using Microsoft Excel as a tool. So by Monday of the 8th week, make sure that you have completed discussion 4 and have completed the Chapter 7 web assigned homework. And by Friday of the 8th week, make sure that you've watched this Chapter 8 lecture and completed the Chapter 8 lecture form. Our discussion on Chapter 8 will focus specifically on confidence intervals for one population mean. And we'll go through a couple of examples on how to do that using both what's called the normal distribution and the student t distribution. Well, the first question that we might ask about confidence intervals is, why would we need such a thing? So let's say that we go through and get our sample of 100 students at New England Tech and find their height in order to make an estimate of the height of all college students in the United States based on our sample of 100 students. And let's say that we find that average height is 67 inches. Well, if we say 67 inches is our height for the entire population, we're making what's called a point estimate. A point estimate of a parameter is the value of the statistic used to estimate that parameter. So in the case of our height, that one sample will represent the entire population. Now, will it actually equal the population's mean height? Maybe and maybe not. We have all kinds that we can take a different sample and find perhaps a different mean height. And in each of those samples, we might ask ourselves, how good is our point estimate? But is that the only way that we can estimate using a sample? Well, the answer is no. What we actually use is called a confidence interval estimate. A confidence interval estimate, rather than being a single number, gives us an interval over which we can say that the parameter in question, let's say the height of all U.S. college students, is within that interval between two numbers. So it's an interval of numbers obtained from a point estimate of the parameter. The confidence level is the confidence that we have that the parameter lies within that confidence interval. And a confidence interval estimate is the confidence level and the confidence interval both together. So we call our confidence interval estimate both together with the interval in which we're saying that a population mean will exist, and the level of confidence that we have that it exists within that interval is going to be our confidence interval estimate. Let's talk about an example. Let's say that we went through and found 25 confidence intervals for the mean price of mobile homes, new mobile homes, based on a sample of 36 mobile homes. So each of these samples, sample 1, sample 2, sample 3, each sample consisted of 36 new mobile homes. And we got a mean for each of those samples. So in the first sample, the mean was $65.45. We're going to say that's in thousands of dollars. $65.45, right? $65,450,000, right? So what we're going to do is $65,450 for the mean of that sample. Our confidence level, we make an estimate, an interval estimate, and say, well, the actual cost of the population of all new mobile homes is somewhere between 63.05 and 67.85, right? Now, in this example, let's pretend that we've found through other information, perhaps a home buying association or U.S. government statistics, that the actual home price for a new mobile home is $65,000. All right, so that is now our estimate. This is now the actual population mean, this $65,000. Is our population mean within the interval? Well, yes. Yes, it is, right? We see that if we drew our estimate where the middle was 65.45 and the low end and high end of that estimate are shown here, right? For our interval, right, we've got an estimate that does contain the population mean. Even though our actual sample mean was off from the population mean, the interval contained the population mean. Now, we redid this experiment 25 times. And 1 out of those 25 times, we found an estimate that was not within our interval, right? 67,000, 7,300, and the 730, pardon me. And our interval went from 65.33 to $70.13 thousand. So right here, we're out. But if you count that up, right, that is 25 samples, one of which is outside the interval. So when we say a 95% confidence interval, what we mean is that 95% of the time when we come up with an interval using this method, which we'll show you, 95% of the time we can be assured that our population mean is actually within the interval that we've found. Perhaps 5% of the time it'll be either way too high or way too low. So how do we go about finding confidence intervals for one population mean when the standard deviation of the population is known? Now, this may seem like an unusual circumstance. How do we actually know what the standard deviation for a population is? In theory, we can actually go through and find a lot of situations where that's true. One situation, for example, would be in the manufacturing of bottles, let's say, or in manufacturing of goods. Sometimes we have machinery that on the assembly line outputs a certain amount of machinery, and we happen to know what the population standard deviation is for that output. Well, that would not be an unusual situation. And so it's possible for us to have confidence intervals where that standard deviation for the entire population is known. All right, so what does a 95% confidence interval mean? What it means to us is that approximately 95% of all the samples have standard deviations of the mean, right, within 2 standard deviations of the actual population mean. Now, if we think about that, right, this corresponded with our empirical rule, right, which our empirical rule stated that 95% of all of our samples were within 2 standard deviations, right? We said that 67% were within 1 standard deviation and 99.5% within 3 standard deviations. Well, those are actually estimates, but our estimate is pretty good. And so we're saying that, well, approximately 95% of all of our sample means would be expected to be within 2 standard deviations of the actual population mean. Now, of course, if we're 95% confident that our mean is actually within that interval, then we are 0.025, that is 2.5% uncertain that it could be too high, or 2.5% uncertain that it could be too low, for a total of 5%, right? Well, of course, that makes sense because it all has to add up to 100%. And in fact, we say that if we are dealing with a confidence level, we're talking about alpha being the number that describes how our probability of being too high or too low. And so the total of both tails here of our standard deviation of our normal curve should add up to that 5%. So when we say a confidence level, we're saying 100 times 1 minus alpha, alpha being this uncertainty number. 100 minus that gives us the certainty, our confidence level. And z alpha over 2 represents the standard number, the standard z value associated with that number within our mean, right? So we're using a z number to help us represent that. So how do we find a confidence level? Well, the process is actually pretty easy. If we get a sample mean x bar, Our standard error of the mean, remember we differentiated that from the standard deviation of the population or the standard deviation of the sample. The standard error of the mean is going to be the standard deviation of the population divided by the square root of our sample size. You recall from our central limit theorem that we stated that this was an important number because it described how our normal distribution about that mean was going to work. So we're going to let z alpha over 2 be a standard normal value determined by the confidence coefficient 1 minus alpha. So when we say 95%, alpha is equal to 5%, and alpha over 2 is 2.5%. And the error bound for the population mean, that is the length of our interval measured from the center to the edge of that interval, is going to be z alpha over 2 times our standard error of our mean. Well, let's do a quick example to illustrate this. The confidence intervals themselves, right, based on our confidence level, is going to vary. Now, when we said 95%, we were saying approximately 2. In fact, from our table of values, if we find 0.05 and divide that by 2, so 0.025, and you go to your table, the z value associated with that is 1.96. Likewise, if we went to 0.05 on our table for a 90% confidence interval, 1.6545 is our z value. And for the 99% confidence level, if we wanted to be very accurate, right, we would say that 2.575. And what we'll see is that there's a trade-off between our level of confidence, how confident we are that the actual population mean is within that interval, and the actual interval itself, how big it is. And as we go from a lower confidence to a higher confidence, we get a wider and wider interval based on that. All right, well, first of all, let's go through an example to illustrate this. Suppose that a sample from a normally distributed population has a mean, sample size, and population standard deviation given as 25, sample size of 36, and a standard deviation of 3. We're saying that x bar is normally distributed with a mean of 25, and our standard deviation, that is our standard error, is going to be 3 divided by the square root of 36. Well, 3 divided by 6, that's 1/2. So to find the 95% confidence interval for our population mean, first of all, we're going to use our confidence level of 1.96. So we're going to come over here and we're going to, for this 95% confidence level, figure that this is going to be our z value that we're going to use here. So our error level would be 1.96 times 3 over the square root of 36, which is 0.98. So our error bound of our population is going to be 0.98, meaning that our estimate for the mean will fall within 0.98 of the sample mean of 25. So to express the endpoints of our confidence interval in terms of the point estimate and the margin of error, which is our mean error bound for the mean, we're going to take 25, the sample mean, minus that error bound minimum, EBM, right? 25 minus 0.98, and 25 plus 0.98, and state that the population mean will be estimated to be between 24.02 and 25.98 in this population. So if we think about the confidence level at alpha equals 0.05, so both alpha over 2 must add up to 0.05, the confidence level of 95% is in the area shown here in the middle. And we're going to use our error bound minimum for the error bound for the mean to develop our confidence interval about the mean on each side of the curve. And alpha over 2 is the probability that our actual population mean is too high or too low based on that sample mean. And in our example, that means that our confidence level of 0.95 corresponds to alpha over 2 of 0.025. That is, we have a 2.5% probability that we are too high or too low, and that our actual population mean will be between 24.02 and 25.98 as shown in this drawing. Okay, more to come.